I am Akarsh Upadhyay and I have recently graduated from IIT Jodhpur. I have an interest in machine learning and exploring various bits and pieces of deep learning. So I was exploring more about this Falcon and Llama, which are currently some of the popularly known large language models. And one of the basic building blocks of which they are constituent is the position embedding. Since this all are somehow modified form of transformer architecture, which actually frames the problem as a sequence to sequence problem. So uh, one of the basic constituents of this a large language models is actually the position embeddings, right? And when we explore the code base of them, as for an example, this is a Falcon, we see that there is a rotary position embedding, and similar is the case with Llama as well. So that's why I thought that let's go get into a deep dive of what this actually is rotary position embedding and from where does it come from. So here is the paper is here. It is actually named as RoFormer Enhanced Transforms with Rotary Position Embedding. Uh, Paper link is here, and we would be actually going parallel with slides as well as the paper. So yeah, let's get started. So, what is the significance of this rotary position embedding is actually can be seen from the Falcon as well as Llama models, right? Where both of them use rotary position embeddings. Actually, both of them are not same, but somehow modified form of each other. But the basic idea remains rotary position embedding. So yeah. So where does position embeddings come in transformers, and what is the actual significance of them? So yeah. So this is the picture which is taken from attention is all you need paper. We see that there is a input embeddings, and then we firstly take a extract the word embedding for each of. Firstly, what we do is we actually take the words, we tokenize them, assign some numbers to it, and then pass it through the word embedding, so that we now got the word embeddings of this sentence. And then for the sake of position, we apply a position embedding here, which is seen here, right? So the significance of position is that to actually provide transforms with the ordering, since the ordering of the word can actually make difference, right? One word no, if present somewhere, can make it a positive as well as a other way it can be make it as a negative. So that is the thing. Then what we actually do is that now since we got position embedding as well as the addition of position embedding and the input embedding, we pass it through multi-head self-attention network. This is the encoder network, and then here we are decoder. So here is the role of the position embedding, right? So yeah, that was it. So we would be actually going to what the abstract of the paper is, and then what are the recent work that have been done in the field of position embeddings, and then we would be exploring more of the paper. So yeah. So what the abstract of the paper says is it enables valuable supervision for dependency modeling between elements at different positions of the sequence. The proposed rope encodes the absolute position with the rotation matrix and meanwhile incorporates the explicit relative position dependency. So it's a bit, I would say, um, com- uh, difficult to understand for me as well when I was going through it in the initial stage. But yes, hold on with me and we would be solving it too. Rope enables valuable properties including the flexibility of sequence length, decaying inter-token dependency with increased relative distance, and the capability of uh, equipping the linear self-attention with the relative position encoding. So this is the abstract. No need to be worrying about it. And then now let's see what are the earlier works which have been done before this. So this is rotary position embedding. Before that, the first absolute position embedding was introduced in the paper. Attention is all you need. Where what we do is that suppose there are actually um, here it is defined as the I8 for the I8 token and the feature obtained at 20th position. The value of the value of that position embedding would be sine of k by dot dot dot, right? K is a constant which generally is taken as one, and for for the position position embedding value at ith token and 2t plus 1th feature, it would be this. So as you see that if you visualize it, like just a second, it as if you visualize it, it's seen something like this. So here the y-axis determines the position and the x-axis determines the depth means this feature. So why this actually was done? We choose the authors in the paper says we choose this function because we hypothesized it would allow the model to easily learn to attain by relative positions. Since for any fixed offset k, position embedding at position plus k can be represented as a linear function of position embedding of position of k. So it's most like the property of sinusoidal wave. More of this I would recommend to go here because here prove what this actually says. So this was the first part where the authors introduced absolute position embedding, and then the second part is that in the second work, relative position embedding, what the authors said is that not all the relative positions between the words is necessary. As for an example, the word at k, relative position of that k plus something to k minus something should be enough for generating a meaningful embedding. So here is what this is. In this work, we present an alternative approach, extending the self-attention mechanism to efficiently consider representation of the relative positions. They clip the relative distance with the hypothesis that precise relative position is not useful beyond a certain distance. So the first was absolute position encoding. The second is relative position encoding. Actually, there is a terminology difference. Encoding is related to this absolute sense. So these are not learnable parameters. It's not. It's kind of my understanding, um, because there are some papers which say encoding, some says embedding. So I'm not sure what to say. So one of the other thing is l- learnable position embedding is the third thing. It's like you apply um, word embedding, you initialize a embedding layer for the position. So these were the two earlier works. Now now here is what comes into play. So this is actually related to the same paper, relative position embedding. So what they did is in the attention formula, the thing is simple. As I mentioned earlier, that you get word embedding and you add a position embedding to it, so you get X. Now this is passed to multi-head self-attention network. So here is the thing: you apply a query matrix to the weight and a key matrix to the weight. Take the attention. This is a softmax normalization, and then you calculate the final value vector, right? So here is the thing. In the in this paper, relative position embedding, what they did is they didn't apply position embedding here. They applied the position embedding part here, relative position embedding part. So you see that there is just a attention formula difference, and here is key as well as value. So more on this, we can find it in the paper as well. So here is the thing. Now let's coming to the third part, which is the method which the authors prepare. So till now, what we have seen is that rotary position embedding are being means what is the significance of rotary position embedding, because they are currently used in LLMs. The first part is abstract. The second is the current methods which have been introduced, and this is the third, which is the proposed method. So in the proposed method, what they say is we take inspiration from the first and the second part, that is the sinusoidal part, and the second, which is the relative position part. Right. So as you would see that as we would be going further, you would see that actually this they prove with the experimental values that both of the first and the second techniques are being captured in the third part. So here is the thing: we hope that the how they formulated the problem is, we hope that the inner product encodes position information only in the relative form. So we know that in the attention part, we see that here is a this is actually an inner product, right? So this is the thing. So here what they say is ki we hope that the inner product encodes position information only in the relative forms. That is, if we take um, two values. Suppose there is value at position m and value at position n, then we actually get a value which is a function of these two and the difference relative position between them. So the ultimate goal is to find an equivalent encoding mechanism to solve the functions to confirm the aforementioned relationship. So a bit of maths, because I come from maths background. So a bit of maths and then we can go for. So here is the thing. Current in the transformers network we currently see D is actually 768 or more than that, depending on base transformer or the last transformer. So they start with a simple thing that let's take D equal to 2. Then we can extend it to D equal to 768 because it's an even. Any vector can be represented as a magnitude and the angle, right? So this is the magnitude and this is the direction. So here is the thing what they do. The inner product of these two should yield a positive value, right? So let if we take the inner product of these two, then what it comes is yeah, this the first part and the second part's conjugate, right? And taking the real product of it. So yeah, that's simple. So this is the thing we need to take the real part of it, and this is the function what they try to define out. We can further write f of q comma k in a multiplication matrix. Similarly, G can be viewed as a matrix and thus enables solution formulation in section 3.1. So here is the thing. Um, I'm not sure much about the maths now. I think that I was able to understand till here. Um, yeah, we can further write f q comma k in a multiplication matrix. That's it. And specifically, this is the main point which I would say. Specifically, incorporating relative position embedding is straightforward. Simply rotate the affine transform word embedding vector by amount of angle, multiply multiples of its position index, and thus interpret the intuition behind rotary position embedding. Um, a bit technical, but yeah, I wanted to share it. So this is the thing which actually is mentioned, that as you can see that as the relative distance increases, the value of this upper bound, the magnitude decreases, right? This was the point which was mentioned in the second technique, that relative distance upon a certain distance is not actually needed. So this is what it also does, right? And in the initial part, it focuses more. Note that the value of this decays with relative distance m minus n increases by settings. And these are some of the evaluations of rotary position embedding in language modeling, where we see that in the mass language modeling, both of them converges. RoFormer and BERT converge. But here, I think that BERT is actually initialized. RoFormer is nothing but just transformers with the. I think the only difference is in the position embeddings part. Nothing more. Attention remains the same. And the same goes with this performer with or without. Performer is one of the other. I think it's linear attention. So it means performer is transformers and linear attention. That's it. And the limitations of the work. Actual limitation of the work is that we provide theoretical grounding as well as promising experimental justification, but um, still there is a lack of thorough explanation on why it converges faster than baseline models. And although we have proved that our model has favorable property, our model shows superior performance at longer text time. We have not come up with a faithful explanation. So that's the thing is it's more like the mathematical explanation is not mathematical, or actually the overall explanation is not so intuitive to say that why the performance is better when we take this embeddings as such. That's yeah. One more thing that uh, let's see this. Let's not ignore it. So here is the thing, that f of q of x m comma m equal to this part, right? So this can be actually represented as some cosine, so the what we say sinusoidal function, right? So here is the thing. This is actually x. So we can either it can be here. The ordering of this doesn't matter, right? So what we actually do is this is actually represented in this form for two-dimensional case xm, and this is the feature, and we have a n by n matrix, and if we multiply it we will get an n by 1, 2 by 2, 2 by 2 to 2 by 2. 2 by 2, 2 by 1, and when you multiply again, it would yield a 2 by 1 matrix. So this is actually a value. This matrix comes from the rotation part. You see that when we actually rotate it from here to here, this is the matrix which is applied there. So yeah, this is how the rotation is being done. I think I think I also need a bit of more understanding on this. I wanted to share. So yeah. So this was the explanation part, and I wanted to also share how can we implement it. So let's just start from scratch, and then we can do it. So here is the thing: implementation details. Hmm. Yeah. So this is the thing. Rotary function to a given value x can be defined as this, that point. This represents pointwise multiplication times this plus this. Right. So this is the how we define it. Now here x comes from the word embeddings part, where I said that it would be word embedding. We would tokenize it and then pass it to words. So let's implement it like this. Collab. So my basic assumption would be that we are actually working on this part, right? This position embedding part. So we would be getting a tensor of shape like sequence batch comma sequence comma hidden feature, and then we would be doing something to apply the position encoding, and then yeah, this attention part would be like it would be a simple attentions which we can cover in some other video. So let's start. Okay, import torch, import. So we would be currently importing the libraries, and so PyTorch code, normal code, and I need to turn this device equal to cooler, and so the basic assumption is word embedding we have is of the shape batch. Let's initialize it here then. Initializing word embedding. Batch size is equal to 1, sequence length equal to 256 or 512 we can go with. And hidden dimension is okay. Hidden dimension is 768. That's it. So we would be currently getting our word embedding, sequence length, hidden dimension, and 2. So this is the first part. Okay. Now let's implement the rotary embedding. So eh, so when we come to the paper, it actually mentions about this m theta. What is it, this m theta? So where does this theta come from? So, let's break it into two parts. Where does the theta come from, and where does this m come from? So this theta is actually inspired from the original attention paper, where we say that. Mm, just a second. Here is the thing. Where did it go? No. Yeah. So here is the thing. We set theta I equal to predefined parameter theta equal to 1000 to the power I minus 1. So I minus 1 is 0 to d by 2 minus 1, which is actually 0 mixing times divided by d times 2, right? So it would actually be resulting into d by 2 parts, and since we would be like replicating it, it would actually become d. So let's start it and then we would be making things clear. So what would be needing as a parameter? D is actually the sequence length, right? So we would be needing the sequence length, and divided by D. No, D is not the sequence length actually. It is the hidden dimension. It has nothing to do with sequence. So here is the thing then. So what we can do is we need to define theta, right? So self dot theta equal to 1 divided by 1000, 10,000, right? Times we need is, so actually it comes down to 0 to something like that, right? Because I minus 1 is actually equal to 0, 1, 2, 3, 4, 5, 6 up to d by 2 minus 1. So multiplying it by 2 actually yields out 0, 2, 4, 6, 8. Right? So we can do it like this. Torch dot a range 0 to hidden dimension by 2. So this is the this part, and we divide it actually by d. D is the hidden dimension. And we need to take the power of it. So I think then this is the part of theta. Now how would we divide the forwarding part? Let's say that we got word embedding. I think that the intuition of implementation is not much clear. But I would try to do as much as I can. And we can improve things further, because this implementation part is like it would take hours to understand, and then it's like, oh, this is how things are. So, yeah, ठीक है. So here is the thing, we got theta, right? And the now they have said that now we multiply it by m. What is m actually? M is that sequence number 0, 1, 2, 3, 4, 5, 6, right? So here is the thing, let's say that sequence length actually becomes yeah, hidden time is actually the int, which is the represents the features of the word embedding, number of features. And what is this? We would be input would be a word embedding of size batch comma sequence length comma hidden dimension, right? And what would be the output? Output would be the same, like tensor of the same shape, batch sequence length, hidden dimension. So what would be sequence? Sequence length would be like this one, right? Dot size one, because zeroth would be batch first, so sequence and second. So let's say now what we need to do is we would initialize the indexes of the sequence indexes, which would be equal to torch dot arage 0 to sequence length dot 2. Since they actually we would be like the devices would be not the same, right? When initializing, let's say dot to device and dot as underscore type. What should be the type of it? Word embedding dot type. Uh, I think its attribute is d type or type. I think it's d type now. Because if the data types are different, the matrix multiplication won't happen. Sure. So now we have the first part comes is multiplying them. So like what we can say something like okay, multiplication, or let's say like this: m underscore theta equal to, this would be of the shape 5 and 2. Okay. And self dot theta would be of the shape mm, hidden dimension by 2. Now what we need to do is m theta would actually be like the shape would be 5 and 2 cross um, this means duplicates, right? Means it would be, if we say unique values, it would be d by 2. Okay. So if we want to come with this, it would be like we let's expand this by squeeze. So this would result into a shape of 5 and 12 comma 1, and when we can have a matrix multiplication of this. So in other words, it would be like 5 and 2 comma 1 cross 1 comma 7 6 d by 2, resulting in 5 and 12 by d by times d by 2, right? And here the thing being, so there is a tricky part here which I have seen in the implementation as well. Ki, since now this part is clear, right? Now if we would duplicate it, so it would result into the same dimension as here. But as we see, ki, our implementation actually covers theta 1, theta 2, theta 3, and so on, right? It's not theta 1, theta 1, theta 2, theta 2. So we can group it like this. Let's say I take the odd ones here. So it would be x1, x3, x5, yeah, x1, x3, x5, and so on. So it would be cos of m theta 1, m theta 2, m theta 3, which actually matches our formulation as well, right? And then so the thing would be we would get sine theta m theta 1, sine m theta 2, sine m theta 3, right? And the last part would be x2, x4, x6, like that. So let's understand it in this way. um, if we group it together, one part would be x1, x3, x5, and so on, and the counterpart would be minus x2, minus x4, and so on, right? So minus x2 would be like, if we see it by index, it would be one third 5. So let's say it like this. What this actually rotate half does is, we would be actually for, we have currently x1, x2, x3, right? But we need to like we need to collect this negatives part together and the positive parts together. So let's do it like this: return torch.cat negative of comma Mm, I think it makes sense. But what I am actually doing is, we would be getting a batch, right? So we need to group according to the positions. So that's why what I have done is, take the odd ones first, add to it and negate them, because you're getting minus x2 minus x4 minus x6 like that. So position it would be minus 1, like the minus x, like minus first index minus a third index. So this is the thing, and then the remaining part is this. So now what the thing being, so we, since we have done this, so now this part is clear, right? Thing, this is not feeling confident. Okay, I would anyhow do. So, and here also what we can now do is, this is of the shape. So this is what we did as a duplicate. Key m theta 1 m theta 1 go on. What we did is m theta 1 m theta 2 and so on, and then we again did m theta 1 m theta 1 m theta 2. So I think then, I think this should work then. We would be getting, and now what we can actually do is, the single position. So, what I have done is, let me make it clear. I understand that it's been, I am quite, but I'll explain what I have done. Uh, oh, same thing. X is not defined. Mhm. It works. Okay, so let me understand. Let me make you understand what actually. So here is the thing that we would be getting a batch word embedding of shape batch comma sequence comma hidden dimension, right? So what I have done is, if you would group these things together, we would get x1 x3 up to n times cos minus x2 x4 means rotating that half part, taking the negation of it and concatenating. So here the same thing I have done here. For let's say for the first part, what we can do is ki first take the odd ones out and then even ones out, concate them. So the actual position would be x1, x3, x5, so on, x2, x4 like that. Times we can cos is the duplicate part, right? Cos m theta 1, cos m theta 2, and similarly cos m theta 1, cos m theta 2. And then at the same time, it would be minus x2, minus x4, minus x6, and so on times. And then the third part, second part would be x1, x3, and so on. So that the same thing would be happening here as well. So here is the thing. Firstly, what I have done is for n theta, if we take likewise I said, right, we would firstly take the even ones out. Just a second. We would be taking the even ones out. So here is the thing what I have done. We would firstly take the we would be taking for all batches. That's why I have done. And then we would take the odd ones out, concate them, and multiply with the cos. Right. And similarly, and for the rotate half, the same thing is happening. Like first of all, take the odd ones out, negate them, and then concate with the even ones. Take the sign of them. And the other thing was, actually this should be a shape 5 and 12 comma d by d, right? But we have a shape of like batch size comma sequence range. So for broadcasting purpose, what we have done is we have unsqueezed it on batch axis. Um, yeah, that's it, and we're good to go. So the one of the other thing is that since we have currently implemented it, I've seen some more implementations as well. So the thing being, actually one and two are not the indexes one and two here. So it can be anything. It means anything. What I mean by anything is you can club first sequence index number zero with index number d by two as well, or the so that's the thing, right? So that is how some of the other implementations have been done. Like I've been seeing many implementations, but the most closest which I have seen current to this is from this bird killers. I think that this is from comes from the official paper as such. So yeah, I think that is. So if you would see for this, what they have actually done is see, the same thing is being done here as well. So query is actually the like query is for the embeddings part, right? Suppose means like we are solving it for one thing. If I bring here two things, then this would be similar to what is being done here. So here is the thing. Firstly, we would be getting the cos and the sine, and then multiply it. That's it, simple. So the only thing we also saw that the word embedding part actually comes into play only here. Right? If I am able to generalize, if I am able to get this, defined into a function, it would be similar to what is being done in Rotary. Yeah. So sequence length is something which we can get, and let's see here. So total length is sequence length plus past key sequence length. So let's make it zero, right? So here, and how are these being self dot cost and self dot sign being cached? So let it go. Yeah. So here is the thing. Firstly, they would like in arrange according to the total length, which is being done in our case as well. Here is the thing, and then what we actually do is they multiply them. Like T is that sequence part, and J self dot inverse frequency comes from here. Base value is 10,000 times this. This is the same thing which we have done here as well. And it's not memorized thing. Let me make it like clear. It's not memorized thing, but it is just that when you go through it, you get the intuition of why these things are working. And yeah, then they're concatenated along these dimensions, and then there's calls answer. So this is the thing they have done. But here, as you can see that I have not actually they have not actually rotate half is being done, right? Let's see where rotate half it is. So for the rotate half, they actually has, as you can see it here, they what did is ki, they smashed it into half. Like sequence length, if it is 5 and 12, they have smashed it into half, and then they have rotated it. Right. So that's the thing which I'm telling here, that 1 and 2 are not actually that index is 1 and 2 of the sequence length. It can be actually 1 and d by 2, 2 and d by 3 and d by 2 plus 1. So it would be like first would be mapping to the half 1 second, and then so on. So this is the thing of how the current implementation goes. So yeah, that was it, and I think that yep, this I think I messed up a lot, but I would try to be better next time, because actually this has been a while, but I wanted to made this video. So that's it. I tried to cover some of the theoretical aspects because I am not don't have much background as a researcher. I have much background as a like making things work, exploring things. Yeah. So that's it. So this is how that position embedding part works in all of these llamas. And then the second part is multi-head self-attention network. There are some optimizations in them, but the more or less the attention mechanism remains the same. That you take the query vector, key vector, and value vector, take the attention between the query and the key, and do some normalizations as well if that if there's a stable normalization, and then multiply the value vector, pass it the second block, and then train on some like first in case of LLMs currently it goes through two stages, right? One of them is pre-training, then mask language, no, not mask language, auto-regressive fashion is being adopted. I think MLM is also used, and then the second part is instruction fine-tuning. So yeah, I mean at last it don't take it much from a word of a researcher, because I'm not that, but I tried to share my understanding, and it would get better as things go on. So yeah, that's it. Thank you for watching. Thank you for giving time.